Welcome to the lesson video on classification and logistic regression. As we've talked about, classification is a process of predicting a class label or discrete output value based on input values. Logistic regression is a classification method where we predict the probability of a class label, and it's usually used for a binary decision. Binary decision meaning we have two options, and we're going to decide between these two options. This plot in the lower left shows us an example of logistic regression predicting the probability of defaulting on a loan. And so the way this plot works, the training data is shown in these yellow plus signs. We have a bunch of training data where we know the loan holders did not default, and so these are shown down in the bottom, and because they did not default, their probability of defaulting is 0. And then we have some other training data where we have observations where the loan holders defaulted, and those are shown up here. And because they defaulted, their probability of defaulting is 1. And we try to estimate the probability of defaulting, and that's shown by this blue line. That's our estimate of the probability of defaulting based on balance. So in this video, we're going to talk about how we do that estimation of that probability function shown in blue. So before we get into that probability function, we have to talk about odds. So let's talk about the definition of odds. The odds of event E occurring, or the probability of E occurring, divided by the probability of E not occurring. So let's think about an example. If I flip a fair coin, the probability of E occurring of, let's say, flipping heads is 1/2. The probability of E not occurring is also 1/2, and so the odds of flipping heads on a fair coin is 1. Let's think about rolling a fair die and the odds of getting a 6. So the probability of rolling a 6 is 1/6 because I have 6 options and only one of them is a 6. The probability of E not occurring, or of not rolling a 6, is 5/6. So the odds of rolling a 6 on a fair die is 1/5, or the odds of rolling a 1 through a 5 and a fair die is 5-1 or 5. And so that's what we mean when we talk about the odds of an event occurring. We can write the odds this way: O equals P, P being the probability of the event, divided by 1 minus P. What we often want to work with is not the odds directly, but the log of the odds, also called the logit. It's the natural logarithm of the odds. And so that's given here. So it's natural logarithm of the odds equals natural logarithm of that P over 1 minus P. So let's move this forward to talk about logistic regression. So for logistic regression, we assume that the log odds of the event occurring is a linear function of the inputs shown in the formula here. Now, if we take this and we solve for P, the first thing we want to do is exponentiate both sides to cancel that logarithm. And so we get this here. And then solving for P, it's a little bit of algebra, but that's what you get for P. And so this is our logistic function, and it's going to give us that blue curve that we saw in that first plot. And that's going to be our plot for our probability. And if you think about this, just think about the structure of this function, assuming B1 is positive, as x gets large, this term in the top is going to go to infinity, and as x gets large, this term in the bottom, and it's going to go to the infinity. So as x gets large, assuming that beta 1 is positive, this probability will be approaching 1. So let's talk about deriving the logistic formula. So here's that graphic we saw on the first page, and so to solve for those coefficients in the logistic regression, this is what we do. We assume the probability of the event is given by this logistic function. It's the function we had on the previous page. Now we've written it out for an arbitrary number of P input variables. And then we assume that true observations correspond to P equals 1, and the false observations correspond to P equals 0. It doesn't have to be true, false. It could be any two categories. Often true means in medical fields a disease occurs, and false means it does not occur. So there's a lot of common applications of logistic regression where we want to say, does something occur? And so that's why we often think of these as true. Then we estimate the values for the betas that minimize the error. And the error is this measured by the distance between each data point and its associated place on the graph. So we estimate mean squared error, and it's the square of each of those errors, the distances between those and the graph. And so you can see in this plot here, we have a lot of low error here, and then the plot comes up and minimizes the error when the balance is high. Let's talk about the meaning of those coefficients. If we look at this formula, the log of the odds equals that linear function, we can see that the quantity beta I is the amount that the predicted log odds will increase by when I is increased by 1. So we have an interpretation of how the log odds change. It's similar to our interpretation of coefficients in linear regression. Now let's talk about what we use to extend logistic regression to more than 2 classes. We use this process called one versus rest. Now, logistic regression really most often used on binary decision or 2-class problems. There are other methods that we would use that are usually more effective on multiple class problems, but this process of doing one versus rest is common, and it's worth walking through at this point. When you have a prediction algorithm that's set up originally to detect a 2-class problem, and you want to extend that type of 2-class problem to multi-class problems. Okay, so we have our classification problem here. I have 3 different classes shown on the plot here, blue, green, and red. And so what we do is we do one versus rest, meaning we take one of those classes and we're going to predict the probability of that class versus all the rest of the classes. So we'll make our prediction, our probability function P1, which will be the probability of blue class. Then we'll take the green class and we'll do the probability of the green class versus the rest, and we'll call that P2. And then we'll do the one versus rest for the orange class, and so we'll predict the probability of orange class versus all the rest. And then we want to create our prediction method that predicts the probability of any of the classes or the class label, and it's given by this formula down here. The class label for an input x is the argmax of pi of x, meaning we just look at these probabilities above, P1, P2, and P3 for observation X, and then we figure which one has the highest probability, and that would be our class label. And we get class labels, class boundaries that are something like what's shown in the plot here in the bottom. With a logistic regression, the separation or decision boundaries between our classes will always be linear. Let's look at an example where we're predicting where somebody did some work predicting wins in NCAA women's basketball. And so what we're looking at is this graduate thesis here. And so they looked at a number of features. The features, so this is women's basketball in the NCAA tournament, and they want to predict the probability of winning in the tournament rounds. And really, this is the first round of the tournament. And so they looked at a bunch of features, and the features that they found were useful were the difference in seed. So when they go to the round, they're assigned a seed by people, observation ranking the different teams. And then they found a second feature that was useful in predicting the probability of winning called DFG, which is the difference in field goal percentages between the 2 teams, meaning just which team had a better field goal percentage or how much better their field goal percentage was. And so this is an excerpt from the paper. This is their logistic regression formula. Here are their coefficients for their 2 different feature variables or input variables, DFG and DIS. And then this is their information about that logistic regression and the parameter values. And you'll see DFG right here. The parameter estimate for the coefficient in front of DFG is positive because the higher your field goal percentage is above the other team, the more likely you are to win. And then the parameter estimate for DIS, which is the difference in seed, that's negative because the lower your seed is, the better your ranking, the more likely you are to win. The logistic regression is very often used in predicting sports events outcomes. It's also used in political forecasting. And often what happens is you get this combination exactly what we see here. One feature, which is or one set of features, which are human determined, sort of opinion based, this DIS, a difference in seed that's determined by people. And then you get one or more parameters that are based on statistics that are computed from the competitors, this DFG, difference in field goal, that adds some additional predictive capability. Review logistic regression. When we are deriving logistic regression, we assume the log odds is a linear function, and then we can estimate the coefficients for the logistic function. Now, it's important to say we estimate them with linear regression. We could solve exactly for those coefficients if things work out proper mathematically. In logistic regression, we have to estimate those coefficients iteratively. There's an optimization effort that comes in there computationally. You often don't see it if you're just using software that does logistic regression. But it's important to understand that when we say estimate regression, the coefficients for the regression. We've talked a little bit about the meaning of those coefficients, and we've talked about extending logistic regression for more than 2 classes. And if you want to remember what logistic regression is, you can remember this plot on the top right. I like to think of a graphic that helps me remember something, and this S-shaped probability shown in blue is the classic goal of logistic regression, estimating between 2 options. Thank you very much.